Hello, this is Rocky Pacelli. This is a short demonstration of the use of machining a Gibbs cam solid model directly on a solid on a machine such as a Mazak Variaxis. What I've done here is I've imported this Parasolid model file, and you see it's nothing more than a block, a vise block, with some angled faces on it, typical for that type of work holder. And also on this face right here, you see we've inscribed the Gibbs logo, and then we're going to pocket that. And to pull that off, what you need to do here is make sure in your machine definition directory, your MDD selection picker, you select the correct machine. In this case, it's a Mazak Variaxis. And what that tells the software is all the capabilities this machine tool has, how many places it can index and where, and all that kind of information. It needs to be known by software before you can really do too much. It's interesting to note here that once you import a solid model, all you really need to do is use the solid itself to tell the software, in this case, where the work planes are. We call them coordinate systems. So to pull this job off, we need the XY plane, or the top plane. There you see the XY plane. We need a plane on the right side on that angled face, and you see I put the origin, a local work fixture offset origin at the upper left hand corner of that face there. There's one also on the left face. Again, the origin is up on the left hand corner of that, and what I call the front, and I put the origin, or local origin, work fixture origin for that face at this corner down here. So with those work coordinates correctly established, all we need to do now is decide what type of tool we're going to use. I think I've used 3 tools for this job. The pocketing will be done, and facing will be done with an 1 3/4 face mill. There you see a 1.75 major diameter, 0.75 shank size, a 0.031 corner radius. The maximum depth of cut here is going to be 1/2 inch deep insert. There's 2 inches sticking out of the holder, and we're going to use tool offset length 3 and tool comp offset 3, and we're going to call it a 1.75 face mill, and it's a carbide inserted, and we're going to use a tool holder. I'm also going to use a 1/2 inch finish mill to go ahead and machine those slots, and we just picked the high-speed cutter from the pull down menu here. Again, it's 0.5 diameter, no corner radius, 2 flutes, inch of flute length, inch sticking out of the holder, and it's also going to have tool length offset 2 and cutter comp offset 2. And to finish the job, we're going to need a smaller tool to go in and do the engraving bit there, that Gibbs logo. A 0.25 radius, a 0 corner radius, a 0.75 flute length, and 2 inches sticking out of the holder. 2 inches sticking out of the holder, and a comp fixture of 4 inches out of the holder. And it's going to be called a 0.25 finisher. So with that done, all we need to do now is bring up the machining palette. You'll see here as we do that, there's the operation. Again, we're applying a pocketing operation. Pocketing from a depth of top of the part, in this case the XY plane being 0. We're going to go from 0 down to the negative value here, 1.9685 is the depth of this slot. And we're going to allow no Z stock, no stepper stock, and I've got the defaults here for the step over. And also I told it here to use the bounding box and use both arc radius into and out of the cut, and clear the surface by about 90 thousandths here. So it's going to go slightly past the surface I selected. In this case, it's that face right there. Do basically the same thing for the faces. I'm going to pick, in this case, we need to tell it in the rotate tab, we're going to do the right face. Again, we're going to go from, say, 3 inches above Z down to 0, because that CS origin is built at that angled face right there. So we're going to do that for both the right and the left face. I'm going to do the same thing for the pocketing operation of those slots. This time we're going to use also a pocketing operation. This time we're going to go from 0 to 3/4 inch deep, 0.25 steps, rotate it in the correct face for both the right and the left. So we're going to rotate it on the left face. And then for the logo, we're going to use that smaller tool. Again, it's going to be a pocketing operation. Negative 0.45 deep with a 1/8 step. And we're going to rotate it into the front plane. So with those tool paths already built, all we need to do now is render it so we can take a look at what the part's going to look like. Let me do a isometric unzoom here, get the job up so we can see a little better. Now we can start the machining of it. Notice how it clears the face I selected there. Got a 0.09 clearance, and it's breaking those corners there a little bit because we have a 100,000 entry and exit line and radius. But one of the really most capable things you can do with this version of software is go into your machine simulation module. And here I'm going to load the machine called the Mazak Variaxis, and somebody's going through the exercise here of building a Variaxis machine model. This probably came from data right from Mazak, and you'll see here this is a Mazak Variaxis 730 SK2, and we've taken the detail right down to the buttons on the control here. What we're interested in, though, is what it's going to look like when we start doing the machining. So with the view cut rendering up there you see our rendering of the part on the machine. And I want to make sure we're going as fast as the rendering can go here. It's interesting to note that this video capture application puts a fair amount of burden on the video graphics, so it slows the rendering down. Probably 50% of would be without using the screen capture video application, so it's a little bit slower than normal. But certainly for training purposes, more than adequate. There you see we've indexed and machined now the left face with that face cutter. I'm going to come and do the same thing with the other face, the left edge face, down to the plane that we're going to cut. Got some clearance issues there on that side. Didn't check that, but for demonstration purpose, you see we're doing a nice job there getting that thing down to size. So we're going to take and machine both of those. I believe they're 42.5 degree angles, but again, when you're applying a tool path to a solid, you don't really need to worry about what those angles are. The software takes care of all that for you. The single greatest thing about working on a good, accurate solid model is you can't possibly screw the part up. You're going to give the customer back exactly what he gives you from a solid model standpoint. So all we're really doing is applying a tool path to their model. There you see now we've indexed to the right face again, and we're going to go in and pocket those slots. I believe they're negative 0.750 deep from each face. So we're taking out, I believe, in 3 cuts, 250 thousandths per pass. Again, the correct index to get the other side correctly oriented. And when it's done with that, we're going to do a tool change, index to the front of the part, and go ahead and engrave or machine the pocket the logo to a depth, I believe, of negative 0.450 in each one of those faces. So from the time that I opened this part as a solid model, a parasolid model, till time that I got it positioned to go up here to this button right here that will bring up the correct post processor for the Variaxis and generate the G code, it took all of about 25 minutes. Even if you have an onboard standalone control at the machine tool and you started this job from scratch, I think it could be very competitive, even with a very experienced operator, because we're starting off an existing solid model, and in addition to that, you can have all these processes saved ahead of time, so you can just recall processes and apply them to new selections of your solid model. So in fact, you could be very, very competitive with the even most sophisticated online applications of any machine tool builder. And one programmer, part programmer, can support a virtually endless number of machines with this concept. Again, The caveat here is working with a solid model for input eliminates most of the issues that you get involved with. There you see the completed part index back to where we can go, so the operator can get the part out of the job. Again, with the addition of the machine simulation module and the model of the machine tool, you can find all your collisions and do all your tweaking without ever fooling around with G-code. It's all done very graphically with drag and drop icons and menus, and with a very limited amount of experience and expertise, you should be able to get good parts in a very short amount of time. I hope this demonstration has been of value to you. If you have any questions, please give us a call. Thank you for your attendance.